reaction where we have competitive inhibition. Let's first write down the reactions. So what we're looking at is an enzyme reacts with a substrate to make a complex. Well, it turns out for competitive inhibition, it means there's some inhibitor species that can also, and this is reversible, can also react with the enzyme to make a complex. And the important thing is that this complex is inactive for making our product. The final step is that the complex can react to recreate the enzyme, so therefore the enzyme's a catalyst, and to make the product. And this has a rate constant K, and we're going to do this at low P concentration. And what that means is then we don't worry about the reverse reaction. So we're going to apply the idea of rate determining step to this system. And what that means is the rate of reaction is the rate of this last step. So the rate that we're making product is the rate constant times the concentration of this complex. Now, of course, we want the rate expression in terms of concentration of things we can measure. And so applying the rate determining step says we're going to assume this first step is in equilibrium. It's quasi-equilibrium. We're going to write an equilibrium constant for the reverse step just because of the normal terminology. And so we're going to say there's a dissociation constant and concentration of E, concentration of S over the complex. So normal equilibrium expression, but for the reverse reaction. We're going to do the same thing for the second step. So then the other piece of information we need to write the rate expression in terms of measurable variables is that the total concentration of enzyme doesn't change. In other words, either enzyme is not bound up in a complex or it's complex with the substrate or with the inhibitor. And then what we're going to do is use the expressions here and substitute both of these into this expression. So let me make that substitution. So now I have an expression that just in terms of concentration of the enzymes, let me factor that out. And so now I can solve for the concentration of E by just moving the term on the right to the denominator on the left. Now, of course, what I want is the concentration of E sub S. And so I can use this equation to substitute in to get the concentration of E sub S, because the concentration of E sub S is going to be concentration of E, concentration of substrate, divided by Km. And I have the concentration from E here, so I can make this substitution. So now I have an expression for E sub S. I can substitute back here to get the rate expression. Let me make this substitution. And then I'm just going to write this in the form that it's more commonly used, and so we can compare to the enzyme kinetics, Michaelis-Menten kinetics without inhibition. So this term we refer to as Vmax, concentration of substrate, and we're just going to rearrange the term on the bottom slightly. So I'm going to keep these two terms in the parentheses, but multiply so that this Km and this Km cancel. And so this last term then is just the substrate concentration. So this is our This is our final answer. Rate expression, enzyme kinetics for competitive inhibition. Both the enzyme and inhibitor compete for the substrate. And if we compare this to the normal Michaelis-Menten expression, so you can see they look similar in what we've done in inhibition. We've added an additional term here. You can look at this now as a new effective Km. So this number, this term in the denominator is bigger than Km, and the rate's going to be slower when we have inhibition.